Decentralize all the things. Decentralize all the things.
Hey there! Welcome to the Web3 Summit Decentralize Now podcast series, hosted by the Decentralize All The Things podcast network. This series features discussions about decentralization from the 2018 Web3 Summit held in Berlin, Germany. This is episode 5, featuring Jordi Baylina. In this episode, Jordi gives an overview of zero-knowledge proofs and how you can build your own simple circuit, which is a small program that can be used to generate zero-knowledge proofs. Thanks for tuning in. We hope you enjoy the show.
Well, first of all, thank you all to coming this early morning for listening this stuff. I think it's a cool stuff, but it's a little... Well, I think it's not that hard. And the idea is to demystify a little bit zk-gas narcs and see how we can create these circuits and how we can really create zero knowledge. And we see that this technology starts to being available. Okay, so I'm Jordi Baylina. I'm from Iron 3 project. In this case, we're working on an identity project that we're using mainly zk-gas narcs. All the development that you will see today, we have done in this context, in the Iron 3 project. So if you have any questions, we are right here about that. But let's start. So the idea of today is just create a real example of a circuit, of a zero knowledge. Just try to create the circuit, create the proof, then verify the proof, and verify the proof on chain, and just check everything that works, everything together. So let's start. First, I want to do a small introduction of what's zero knowledge. I expect that most of you already know. If you are here, probably it's because you are interested on. But I just want to explain you what's zero knowledge from a more practical side. Okay, so the kind of zero knowledge that we are working is quite generic, but there is we have what we call it a circuit. Sometimes we call it circuit or we call it program. Okay, but at the end is a program that in general have an input data and, if you want, an output data. The input data, sometimes we can divide it in private input and public input. Okay, so we have a circuit. Let's see, that's a deterministic circuit. So it's a circuit that you put an input here, and at the output we have automatically a value. For example, if the circuit is just an addition, you just put here, for example, a 3 and here a 2, and at the output I have a 5. Okay, that would be a typical circuit on that. We see that the inputs can be private or public. What we really are proving when we are creating a zero knowledge proof? What we are proving is that we know a private input, that when we execute with this public input, it gives this output. So mainly in a circuit, we just generate a proof. You generate a proof, and to verify the proof, we need to pass the proof itself. Let's call it P, the proof, and we need to pass also, well, of course, the circuit. What we are proving against this circuit, and then we need to pass also the private input. Sorry, the public input, and the output. So the verification, we just pass this function, and this can return true or false. We can only generate this proof if we really know the input. And not only the input, but all the intermediate values here. In this case, in the case of an addition, this is quite easy. Okay? Because if I have a 5, everybody knows two numbers that when we add them together are 5. But imagine that here is a hash function. And I have only one private input, which is the value that I want to hash. So in this case, what I want to prove is that I know an input, I know some value, that when I hash it, it gives this specific output. So if I pass here in the verification, you pass the output that you want. In this case, so the public input is nothing. We don't have public input in this circuit. We have the proof, and of course the circuit is just the hash function. So in this case, we can prove that we know this input at the hash. Let me just put, for example, some example circuits so that we can see that the usage of that. For example, typical thing is, imagine that I have a circuit that verifies a Merkle tree, just a generic Merkle tree. Okay? So imagine that I have a Merkle tree where the leads, for example, are public keys of people that represents people. So I want to prove, for example, one thing that I want to prove is, for example, that as an input I have, for example, a Merkle proof. Maybe I have my public key, my private key, and the output is the root of the Merkle tree. So I just generate a circuit that I give a private key. With this private key, internally I'll calculate the public key. So I do a multiplication, I get a public key. And then I just have different hashes. So I just hash all them together. And at the output I just generate. So with this public key, I generate the keys. If these inputs are private, so what I'm doing here, I am proving that I have a private key whose public key is inside this Merkle tree. But I'm not revealing, because this is a private input, I'm not revealing, of course, what's my private key, nor what's my public key. So I'm one member here. I'm saying that I'm one member here. That's really, it's valid. It's inside here is a valid one, but I'm not saying who is that. That's, for example, very important, for example, for a voting system. The voting system, when you want to vote, you need to be sure that you are in the census. You are in the list of the people that can vote. So if here is the list of the people that can vote, you just get the list, which is public. You get the Merkle proof. You have, of course, your private key. You generate a proof that, of course, you now your private key and this Merkle proof of the place, and then you calculate the root. And anybody can be sure that you have this private key. If you don't have that private key, you should not be able to see that proof. Okay? So these are kind of typical examples of things that can be done. Sometimes are normal operations that don't need to be even private or public, but you are, for example, just to save a space. This is very important, for example, for scaling. I can generate, for example, many transactions. Okay, that I can generate transactions off chain. And then I can prove that I executed those transactions in the right way. And then I just put this proof in a normal, in an on-chain. Well, this is a voting system. It's an example. But for example, in a system where you have a lot of transactions, when you want to scale transactions, mainly is that. So the idea is that you have like a service, an untrusted service that just collecting transactions. They are putting all these transactions in a Merkle tree. And with some logic, so they cannot, for example, double spend or whatever they think. And all this can be proved that is executed in the right way with a single zero knowledge proof. Yeah, the idea of this is that you are proving, you have to you don't solve full scalability of that, but you prove that you are executing something in the right way. Of course, you still have the problem of data availability that you need to solve anyway, but that's another story. But at least you prove here that you are doing the things in the right way. That's one thing for. So one thing for, and the other is just because you are proving that you are executing something in the right way. It's just proving that you are executing a specific circuit that in the right way. You don't care about the inputs. You don't care about what transactions, but you know that you executed the transactions are correct. This is it's just an example. Probably it's not the best example. I know that I hear it's probably not the best example for that. I think that Amir just showed you a much better example, much more simple, and probably much more useful at this stage. But there are many. Zero knowledge proof are this circuit can be anything, and this can, for example, be but this could be this proof means just you put some input and maybe you can prove with this circuit that you are, for example, paying the right taxes. But the nice thing of that is that because you don't reveal the input, you are not saying how much money you have and where it comes from and whatever. You are just proving that you are doing the things in the right way, so that you are following. So you are doing a specific calculus. Okay, so there are many applications. There was a good talk right now with the talk about different applications, and it's huge and it's through the computation. There is a lot of applications on that. So what we are focusing in this session, we are mainly going to construct a circuit. Okay, so the first circuit that one could construct is a very simple circuit. The circuit that we will generate is a circuit that we are able to factor a big number. Okay? So that means that given a number, for example, if I give you 33, so please let me know what two numbers, when you multiply them together, it gives 33. In this case, it's quite easy because it's a small number, and everybody already thinks that 11 and 3 gives 33, so it's quite easy. But if I give you a huge number, 256 bits long number, this is quite more difficult. So mainly the circuit that we are going to build is quite simple. So the circuit is going to be, let's do a circuit. The input is going to be, let's say, A and B. These are going to be private inputs. Let's put here private. And the output is going to be public, okay? And this is going to be just the multiplication. That means that if this is C, that means that C equals A times B. So this circuit is going to be only valid if I have two numbers. If I know two numbers that when you multiply them together are C. But of course, without telling you which numbers are A and B. That's I'm proving that I know those numbers, but I don't want to tell you those numbers. So we are going to build a circuit. Here, the circuit, there is a trick. We are going to solve at the end of the session, but just because I'm sure that somebody is asking us, is already asking. There is a trivial solution to this problem, okay? So if one of those numbers is 1 and the other is just C, then you can find it quite easy. So in some way, we need also to prove that none of these numbers is 1. We just, if somebody comes to this mind, just forget about that, okay? 1 cannot be. We will explain later in the session how can we do that. So let's focus first in doing the trivial circuit, which is just as normal and simple multiplication. So let's start. I don't know if you are ready with the laptop. Okay. First of all, I know that some of you is gonna do the stuff. If there is somebody has any problem, here's maybe some people can help on each other. Okay. The first is the prerequisites. Of course, you need to install Node. Just one side note about Node.js is the last stable version is, I think, is 8 dot something, and if you use the last unstable version, which is 10 dot something, it's going to be much faster. And this is quite important in this stuff, mainly because the last version of Node.js it supports native big numbers, big integers. And then the operations are quite faster. So if you install a 10 dot something node, it's much better. It also works with 8, but it will go a little bit more slower. Right? Something like 10 times more slower. So it's an important gain that we get in the number 10. Last version, just as a side note, for example, Chrome already supports the big number in JavaScript. It's like an extension. It's not in the last standard. Okay, but Firefox, for example, doesn't support currently. I don't know if maybe last week they changed it, but it's not yet. Okay, so that's just to know. This is some improvements. Big numbers in cryptography, they are used quite a lot. So it's a good thing that JavaScript start implementing these big numbers. Okay, so the first thing that we are going to do once we have this node installed, so it's not that I expect that most of you already have it, so we need to install these two packages. Circom, which is the compiler of the circuit, so it's a special compiler for this kind of circuits, and then Snark.js, which is just a working tool for creating the proofs, for verifying the proofs, and for all the stuff that's in there. So just make sure that you npm install -g. Maybe some of you have some problems when you install -g because you need some privileged sudo, but if anybody has some problems on that, just let me know for later. Okay, but everybody that knows a little bit of Node, it should be quite easy to install those packages. Once you have these two circuits, the first thing is, well, let's create the circuit. Of course, in a normal situation, you would just create a normal repository and all that stuff. But for this case, just open a directory, an empty directory, and create this kind of hello world. So this is the circuit that we are doing here. Okay, and now we are going to see this circuit. Yeah, it's if you see my Twitter, it's there, but it's iron3.io /blog/Circom and Snark.js tutorial with hyphens in the middle .html. If you see my Twitter, I just published it there like 1 hour ago. So J Baylina. This is my Twitter account. I just retweeted the link right there. Yeah, I will show you later maybe some more complex circuits, so you will see the powerful in there. But yeah, it's what you're saying. In general, you cannot build loops. You can build constant time loops. Okay, so if there is this circuit has like 2 stages. Okay, one first stage we just compute the constraints. Okay, and the second stage that you just compute the witness. Okay, and all that stuff. Of course, you need to be able what are the constraints beforehand. Okay, so it cannot be variable related. Yeah, you can test it in general. It should work. Okay, but just the idea is that already tells you where it's. So you can. Yeah, at the end, the best thing is you think one good thing to think about this is like in electronics. Okay, so you have components, you have circuits, and the idea is that, for example, you have a gate, a normal electronic gate, an AND gate, or an XOR gate. Okay, so give an input and you automatically have an output. If you have a loop, then you will have. It means that you have 10 gates. Okay, we'll see some examples later. We'll see some complex code written in Circum, and you will see more the powerful on that. Okay, just here is just we are starting just doing like a hello world in here. Okay, this is very easy, but I want to run in all the cycle. This is a hello world method. I want to run in a cycle with a very simple circuit on that. So let's see this. So this is a very small circuit, but let's analyze what's this circuit about. Okay, first of all, you see here this is a template. And then you have an instantiation of that template that's called mine. This language, mainly, you can define templates of components. For example, I can define a template which is an AND gate or a NOR gate or maybe another or a multiplier or a binarizing or a hash function. And then even those templates, we will see that these templates can have even parameters. So I can have, for example, another of variable number of bits or whatever. So it's like a template is like a class, is what we understand as a class in a normal. So it does not do nothing, but you can instantiate as many components as you want, and they can be different. The people that know C++, the concept is a template too. So you can create a template of classes. Okay, this is a template of components. And in the last line, we just instantiate. We are instantiating that template. In this case, where this template is called multiplier, and here we are instantiating a multiplier. All the circuits in Circum it's like a little bit like C. They must have a component called main, which is the principal, the main component on that. Okay, and what has this template? Because this template has 3 signals, 2 inputs that are private, and 1 output. That's mainly what we are defining here. Just 2 inputs, 1 output. And we are already telling here that those inputs are private. If we don't say nothing, that means they're public. That's how we define that. And then this program has only one thing, which is very easy. So we just connect the signal C to this A times B. You see here, this special operator is not an equal, because we are connecting signals. Okay, we'll see that we trade different what are signals and variables. Okay, but here is just a normal signal that we are just saying that the C is output A plus B. So here is what we're saying. Here we'll see. Well, this is a circuit. You can just create it. Okay, be sure that's more or less well written. If not, you will get some error later. And let's compile the circuit. Compiling the circuit is as easy as just running circum. And then you just put circuit, your name of your file, circum.circum, -o, and the output is a compiled circuit. It's a JSON, but it's an internal format. So just compile it. It should run. Did anybody compile it? Yeah, more or less okay? Yeah? Okay, great. So we already have the circuit. From now on, we already have used the Circom, which is the compiler, and now we are start using Snark.js, which is the tool just to start using this circuit for. Of course, you can do a snark.js.help. You will see all the options there. Mainly is the best documentation that's written right now, just doing this help. And the first thing that we can do is, for example, you can run a snark.js. Well, you see, for example, info and the name of the circuit. You can avoid if you want the circuit.json. By default, it looks for a file that's called circuit.json. If it's different, you can put different. But if it's called circuit.json, you can just avoid the -c and just do snarks info. And it should give you some parameters of the circuit. In this case, should be two private inputs, one output, one constraint. Very easy circuit. General circuits have millions or even billions of constraints. That's a little bit internally how the circuits works, but at the end, we have a circuit, but when we say that we are proving a zero-knowledge proof, what we are really proving is that those signals, inputs, outputs, and maybe some internal circuits, they follow some constraints. In this case, for example, the constraint is that C must be equal to A times B. So when we are building a circuit, when we are saying that we are compiling a circuit, one of the things that we are doing is mainly looking for those constraints and creating this list of constraints. Let me give you, for example, some examples, okay? And here of some interesting constraints. One interesting thing to do is, for example, here, for example, you see a constraint of an XOR. The constraint of XOR means that Xout, so the output, must be equal to A plus B minus 2AB. Okay, this is a constraint. So you have an XOR means that the inputs must follow this function. Of course, we understand as binary, but if you see that when A and B are both ones, this means that this is 1, and then it's 2 minus 2, this is 0. Okay? When one of those is 1, this term is 0, and the other, of course, is 1. Okay? And when all other zeros, this is 0. So you see that this circuit, these constraints follow a normal XOR, follows a normal XOR circuit. Of course, this is only valid when the inputs are binary. But here in the Circom, all the signals are not only binary; they are a number between 0 and the order of the curve of Zk-SNARK, which is this number is close to 253, something like that. Okay, so it's a huge number. For a normal circuit like XOR, this would be one constraint, and probably we also want to create another constraints to force these signals that are binary. So in this case, for example, we should add, for example, that to be a binary, I can say that I minus 1, this must be equals to 0. With a constraint like this, I'm forcing that this equation is going to be only valid when A is 0, because this term is going to be 0, or when A is 1. If it's something else, this constraint is not going to be valid. Okay? So if I want to create a single XOR, what I need to create is I need to create these two constraints. When we are creating, just compiling a circuit, one of the things that we are doing is just generating all those constraints. This is a very important concept. Let's move on. If you want to see those constraints, you can just do print constraints on your circuit. You will see that you have a single constraint. Maybe you will see that the format is a little bit strange. It's not it's not the usual way that we're used to read, because we are in Zk-SNARKs, we are putting all the constraints in a specific format. Okay? I just print you the format because I think it's good to see it at least once. In general, the generic form of constraints for a Zk-SNARKs, we put it in this way. Okay? So A1, which is A11 S1 plus A12 S2 plus SN, AN SN, all that times B1 S1 plus B2 S2 plus BNSN minus C1S1 plus C2S2 plus CNSN. This equals 0. Okay? And the same thing for A221S1 plus A22S2 plus A2NSN times B1S1 plus, B2S1 plus B2 plus B2NSN minus C2NSN plus C2 this is C1 no C2N C2 C 3 1 N. This is C2N C 3 1 2. This is B1 2. This and 1 and 2, and then this is C1 1 C1 2 C1N, and this is C21 C22, and this is C2N SN equals 0. Okay, and then just as many constraints as we want. Okay, but we put it in this format. Okay, this is, we call the term A, this is the term B, and this is the term C. Okay, these are linear combinations of the signals. Okay, the signals are the one that's variable, and A1, A2 are parameters of the circuit. Each circuit has this A1, A2, B1, B2, these coefficients defined. So at the end, you see that compiling a circuit means just finding these matrices of coefficients and all that stuff. Okay, we already have the circuit. We see the circuit compiled. And now we have to do something that's very specific to the ZK-SNARKs. And this probably is the biggest criticism that has the ZK-SNARKs. ZK-SNARKs, I would say that it's a perfect technology except for this trusted setup. Okay? ZK-SNARKs, they require, and this is quite specific to this technology, they require that for each circuit, we run what we call a trusted setup. That means is that we need to get some random values, do some computations on that random values, keep the computation, so keep those values, but the initial random, the seeds, the initial random, some toxic values, we have to throw it away. And we need to be sure that we throw them away. If we don't throw them away, that means that all the system doesn't work. Okay? And this is a famous trusted setup. Here is what, for example, the Zcash people, they use these ceremonies and all this story. And this is a full topic just by itself, how to solve that. But it's a problem that once we solve, I would say that that's happened. But this is also the biggest criticism, okay? Because at the end, we end up having to trust this initial setup. There are some interesting solutions for that. It's multi-party computations and some trusted hardware, or just people just drilling computers, and there are things. It's a very mystic thing, but that's important to know. Okay, so what we are doing here is we're just running a trusted setup. It's a trusted setup because you trust yourself. Okay, so it's not a very good thing here. This should be running in a different way, but at least to start working on that, we just need to generate those parameters in our computer. So just run the trusted setup on here, and after you run the trusted setup, mainly what it does, this setup, is generate two files. Okay, one proving key and one verification key. Okay, this is the result of the trusted. This is the result of the trusted setup. We will need the proving key to generate proofs, and we will need the verification key to verify that those proofs are valid. Run it. Hope that everybody should see the files. By default they are called this way. Of course, you can change the parameters and change the names and all that stuff. Okay, but you should see those keys somewhere in that place. Here is a research topic, and there are some works that maybe it's for some circuits like that. Some of them divide this trusted setup like into steps. One shared important with many people and very trusted setup, and then small setups that are not so necessary for security. And there are setups that you can just like add like entropy of that people can do the entropy just by adding new information. There are different topics. It's a topic research. It's something that it may change in the future, but right now I would say yes. So for each circuit needs its own setup. So for each circuit you will have a verification key and a proving key, and you need to be sure that the toxic values are thrown away. So we already have run this ceremony of drilling computers and being sure that we don't know these toxic values, okay? And we have this result, the proving key and the verification key. So now, next step is to generate the proof. But before generating the proof, what mainly we need to do is like execute the circuit. We need to know all these signals, and in this case, in the case of this is very trivial because we have only 2 inputs and 1 output. So mainly what we need to do is mainly compute the output. Okay, that's the only thing. But when we have an important circuit that we have very intermediate signals, imagine a hash function. You need to do a lot of steps in this. For example, if you have here maybe you have a door, and then you have like another door. Okay, and then you have here maybe another door. Maybe let's put here an XOR. Here in a circuit like that, you see that, of course, you put an input, but you need to calculate all these intermediate signals that are in the circuit. These signals, or sometimes they call it wires, okay, because wires of a circuit. This also, the full set is what we call it the witness, okay? This witness is all this information that we do, when you execute the circuit, when we do the circuit, it's like we plug the circuit and we just have some values. And this is important so we need to do that every time that we want to generate a proof. Mainly, if we see from the constraints, is we are just computing all these signals, all these variables that we are sure that matches all the constraints. Okay, but we need all the signals, inputs, outputs, and intermediary signals. We have the full set. We know how the circuit is at all. This is what we call the witness. So the first step is compute this witness. Okay. So to calculate this witness, first of all, we need we need an input. Okay. This depends on the circuit. So first of all, we need to tell what's this going to be this input, this witness. So we just need the inputs of the circuit. So let's create a file which is called input.json and put the input signals, in this case, something like that. Of course, you can put the values you want there. This is just an example. In this case, for example, I have a NAND. So imagine I have four inputs, okay? So imagine that here I put a 0, a 1, and a 0. Okay, this is the input of the computing the witness means this is 0 and 0 is 0, none. This means that this is a 1. No, in this case you are not throwing away nothing. You are just executing you are executing the circuit. You are executing the program. So that means that you are putting an input into the circuit and you are computing all the intermediate steps and of course the output. So you are just executing this, but you need to keep all the intermediate states, because at the end, what we are proving is that these intermediate states, that are the signals, they match all the constraints that we defined before. Now the ceremony we already did the ceremony. We already burned this is done. Okay, but then the ceremony, we know that this is only not needed for one circuit. Okay. You don't care what input and what output. You have just the board. It's like this. And of course, once we have the circuit, we can generate as many proof with different values as we want. But we need to do it. This trusted ceremony, we need to do it when we design a new circuit. Once the signature is designed and the people start using and generating proof with different inputs and different outputs, you don't need to do the trusted setup again. Of course, you cannot use the same proof for different circuits and. Yeah, sometimes there is some tricks. That's, for example, the trusted ceremony of Zitka Snarks is already done. Sometimes what I do is I may use this circuit to run it in a specific way. Maybe it's putting some inputs to 0 or just using some parts of the circuit in some way so that I don't need to run this trusted ceremony. But I'm not but I'm running the same circuit. The only thing is I'm running the same circuit with specific values, and there are some tricks on that. But the circuit is the circuit. You do the trusted ceremony for that circuit, and that's attached to that circuit. So the verification key and the proving key are attached to that circuit. Yeah, this is what we call it embedded. This is very interesting, but it's hard. Yeah, it's hard. Yeah, there are some research on that. Yeah, this is what we call interactive, and this is very interesting. It's interactive. I know rentrancy. So just verifying a Zcash snark inside a Zcash snark. Yeah, this is very interesting, and this is we can talk about later. Okay, that's one of the things that you can do, but it's hard. The problem is that verifying a circuit is it's a lot of constraints. So. Okay, so once we have the input, we just calculate the witness. Okay, you will see that the output is going to be a file called witness.json, and you will see there all the signals. In this case, we have very few signals. You will have 4 signals. In this case, you have A, B, C, and you have a very special signal that's called the unity. That's in the beginning. That's always 1, and that's like a special signal. It's like in electronics, it would be like the power on. The plus 5 volts. You see, for the people that does electronics, that means that. Okay, you need that special signal. But you will see it in all the circuits, and in general, it's the first. At least in this implementation, we put it at the beginning. But okay, once we have the circuit, okay, we already run the circuit, and now we have to actually generate the proof. Okay, so we have the input, we have the trusted setup. So right now, to generate the proof, we just take the proving key, the witness, and with the proving key of a circuit and the witness of the circuit, we generate the proof of the circuit. So if you run that, you will see that this generates two files. One, of course, is the proof itself, and the other is just a subset of the witness that mainly is the public part of the witness. That is only the public input and the public input and the output. Nothing else. We just remove all the intermediary signals and, of course, the private signals. This is the part that you want to pass in general to the verifier. So when you want to verify something, means that you are able to, so you run the circuit where all those public signals, in this case the public output, the output and the public input, are those that we are saying here. This is very important. So, okay, we already have the proof. So now just let's verify it. That's quite easy. Just go verify. To verify that proof means that we need to pass, again, repeating, the verification key of the circuit, the proof itself, and the public input.
Thanks for listening. If you haven't already, please subscribe and give us a rating or comment if you enjoyed this content. This episode was brought to you by Santa and the unicorns at giveth.io. Remember, this podcast is made possible by the donations we receive from listeners like you. If you'd like to help support the podcast, you can do so by donating Ether at dattpodcast.com. That's DATT podcast.com. Please check the show notes for more information. Thanks again for listening, and until next time, keep decentralizing all the things.